Hello, welcome. Today we're going to talk about electric fields. Previously we spoke about electric force and Coulomb's law, and electric fields are very similar to electric force, but they're just slightly different. It's very important to not confuse the two. An electric field is what we call a field force. And a field force is just a force that acts through space. So what that means is that there's no contact between the two objects and that the force just acts through all the space around us. Another good example of a field force is gravity. Gravity acts through space to give us our gravitational attraction. So in other words, if we have an object that has a very, very strong, let's say, positive force, as a result, all around this object, it permeates an electric field. And so as a result of that electric field, any object that happens to be within the field is going to experience an electric force as a result. And so that electric force can either be an attractive force or it can be a repulsive force, depending on what the charge of the object is. This is a big difference between gravitational force. Gravitational force is only attractive, whereas electric fields can create an attractive or a repulsive force. So the way that we can find the magnitude of this electric field, E, is by taking the force that's exerted on the charge and dividing it by the charge itself. So in other words, the strength of the electric field at this exact point is based on the force caused by the object divided by the charge of this small particle here. Now it's very important to realize that this magnitude of the electric field at this particular point is independent of the strength of the charge at that point. We know from the previous section that because of Coulomb's law, the larger the charge is here at this point, the larger the electrical force will be as a result. Because as the charges increase, the electric force increases as well. That is why, in order to find the electric field, we divide the force by the charge itself. This eliminates the effect of the electric charge on the magnitude of the field itself. And so using this same equation, we can come up with our units for the electric field, which are just newtons per coulomb, which we get from this equation. The other thing we can do is we can take this same equation of E equals F over Q and substitute Coulomb's law in for our force. And this gives us K Q1 Q2 over R squared. And real quick, let's label our two objects. We can say this is Q1 and we'll call this Q2, just for notation purposes. And then we divide that by Q2. And what happens is these two Q's cancel out and it gives us a new equation of just KQ1 over R squared. And so again, we can see that our electric force is dependent only on the charge of object 1 and the distance from object 1. And so both of these formulas are perfectly valid for calculating the magnitude of an electric field. It's just dependent on what information you have, which will decide which formula to use. But again, just like in our previous unit, it's very important that we use the absolute value of our charges. We just want to find the magnitude of our electric field, and then afterwards we'll go back and determine the direction of the electric field. So, with that in mind, we can again say that our electric field is a vector. And so because it's a vector, we treat it in the same way that we treat all of our other vectors. And specifically, we treat it the same way that we treat our electric force. So because our electric field is a vector, it means it has direction. And the direction is based on if our charge is positive or negative. The charge that's creating the electric field, that is. So, we have an electric field that goes towards the charge if the charge is negative. And then it goes away if the charge is positive. So, we can look at an example. If we have an object that is very, very, very negative, as a result, our electric field will point towards the object. So it's important to realize that our electric field is pointing towards the charged object, but if we have a particle that's inside that electric field, the electric field that it experiences points towards the object, but that doesn't necessarily mean the electric force is going to point towards the object. The electric force is dependent on the charge of both particles and how they interact. But here, the electric field points towards the object because it's negative. Whereas if the opposite is true, and our object is very, very, very positive, it creates an electric field that moves away from the central charged object. So again, if we have a particle that's inside of that electric field, the electric field that it experiences is away, but that's not necessarily the direction of the electric force that it will experience. And again, the electric force is based on if it's like charges or opposite charges. So let's look at another example. If we have three particles, let's say we have two particles rather, we have a positive particle, and then we have a negative particle. And both particles independently create an electric field all around them. And we want to know what the total or resultant electric field is at a point in the middle of them. So, for notation's sake, I'm going to label this as particle 1, I'm going to label this as particle 2. And so at this central point, if we just look at particle 1 and ignore particle 2, we can say that the electric field from particle 1 is going to go away from it. And so this will be electric field 1 because it's being created by particle 1. Then we can do the same thing with particle 2 and say, well, the electric field is pointing towards it because it's created a negative charge. And so electric field 2 goes towards the negative as well as electric field 1. So both of our fields are created in the same direction. So then from here, we can use the formulas from before. We can say electric field 1 will equal K Q1 over R1 squared, where R1 is just the distance between charge 1 and our point. We can find E2 by saying Q2 over R2 squared. Where again, R2 is just the distance between the point and Q2. So this will give us the magnitude of E1 and E2, and then because of the vector nature, we can say that our resultant electric field will just be E1 plus E2. And again, I'll point out that it's very important that we use the absolute value of our charges and then afterwards determine our direction. The last thing we'll talk about is electric field lines. We've kind of mentioned them briefly, but now we're going to talk about them in a little bit more depth and how they interact with each other when we have multiple objects. So we have 4 short rules to electric field lines. The first one is that electric field lines always go from positive to negative charges. So in other words, if we have a positive charge and a negative charge side by side, our field lines are going to look like such. And we'll put arrows to indicate that they're going from positive to negative. Our second rule is that the number of lines a charge has is proportional to the magnitude of the charge. So in other words, if our charge is very, very strong, either positive or negative, it's going to have more lines coming out of it than if it were a weaker charge. So if we look at this same example from above, we can see each charge has 2 lines coming out of it, which means both charges must be of equal magnitude, even though one's positive and one's negative. So if we had another example where we have one charge that's 2e, and then the second charge, which we'll just say is negative e. So again, they're opposite charges, and one has twice the magnitude of the other. Our field lines would in turn look something like this, where we'd have our smaller charge would only have 2 field lines, or our larger charge would have 4 field lines because it has twice the magnitude. And then again, we can come in and add arrows to indicate our direction. And again, notice our arrows don't necessarily all have to connect to each other. These 2 field lines go off into infinity to connect to some other negative charge that's not shown in the diagram, which is perfectly acceptable. Our field lines don't always have to connect to another charge. Rule number 3 is that our field lines will never ever cross. Our field lines indicate the direction of an electric field at a given point. If our 2 lines cross, then that indicates that there's an electric field going 2 different directions at an exact point, which is not possible. Because they're vectors, there'd be the resultant between the 2, and we can only have one electric field going one direction at one spot. So our electric field lines will never ever cross. So our last rule is that lines will always be perpendicular to the charge's surface. So in other words, when we have our charge, our field lines have to be perpendicular to the surface like such. So this is a positive charge, and we can see that all of our lines should be perpendicular to that surface like such. We'll never ever have field lines that go off at a strange angle like that, because they're not perpendicular to the surface. Similar, if we have a capacitor, which is 2 parallel plates, then our field lines just come straight out across like that. And again, this would be positive and this would be negative. So whatever the shape may be, usually it's circular, our field lines always have to be perpendicular to that surface. So again, let's just look at one quick example. We've already looked at kind of several small examples, but let's say we have 3 charges, 2 of them positive, and then 1 of them negative. And we want to draw our electric field lines for this arrangement. And so we'd start by drawing our field lines from the positive charge to the negative charge, and I'll put some arrows to indicate our direction. But notice we won't have any lines going from the positive to the positive, because they only go positive to negative. And so then I'll go ahead and add a couple more to the sides, like such, trying to make them as perpendicular as possible. But from here, as we mentioned, the number of lines that it has to be proportional to the charge of the object. And so all of our objects here have an equal charge. So each charge has to have an equal number of lines coming off of it. So each one of the positive charges only has 3, whereas the negative one has 6. So we can fix this by adding 3 more charges to each, or 3 more lines rather, to each of these charges, and then we'll add arrows to indicate direction like such. And so this would be our electric field diagram for this configuration. Each charge has an equal number of lines coming off of it. All of our lines are perpendicular, none of them cross, and they go from positive to negative. And so the significance of this diagram is that it shows us the direction and relative magnitude of our electric field at any point within this diagram.